A rational expression is nothing more than a ratio of polynomial expressions. So something like maybe 4x cubed minus 2x squared plus 1, and I'm dividing that by another polynomial, 2x squared plus 5. That's a rational expression. Notice you should always be concerned about the domain of a rational expression because there's the potential to be dividing by 0. In this particular example I've written above, 2x squared plus 5 is never 0 for all x, so the domain is minus infinity to infinity. The reason for this is I'm squaring x, and then I'm doubling it. That's always going to be a non-negative amount there, and then I'm adding 5, so 2x squared plus 5 is strictly greater than 0 for all x. And therefore there's no values of x that I couldn't put into the domain. There's no potential to be dividing by 0. The domain is all real numbers as a result. Compare that with something maybe like same numerator, but now make the denominator linear, 2x plus 5. Now we have the potential to be dividing by 0. If I look at 2x plus 5 and ask where it is 0 so I can rule those values out, I find that x is equal to minus 5 halves, and so I should exclude that value from the domain. So the domain is all real numbers x not equal to minus 5 halves. I can write that in interval notation. I'll start at negative infinity and go to minus 5 halves, and I'm not including it. Then I'll pick up at 5 halves, not including it again, and go to infinity. That's another interval in the domain. And then I can kind of, in effect, glue these two intervals together by taking the union of them. So you're in the domain if you're in this interval or you're in this interval here. And the symbol, this union symbol here, is effectively combining these two intervals into a new set. This is the set of all numbers other than minus 5 halves because we've explicitly excluded that with the parentheses. One of the common mistakes you don't want to fall into making is canceling common terms in a rational expression. Do not cancel common terms. And by terms, I mean things that are being added or subtracted in the polynomials themselves. So for example, here I have a rational expression, and both the numerator and the denominator have a common term of 2x cubed. You cannot cancel that. Order of operations requires you to add everything in the numerator, add and subtract all these terms in the denominator, and then do the division. What I do see in this example are a number of common factors that appear in the numerator and the denominator. So usually it's a good idea to see if you can factor if you want to simplify things. In the numerator, there's a factor of 2x squared in both the terms. So I'm going to take that out. And I'm going to need to provide a factor of x to get me that 2x cubed, plus a factor of 4 to get me the 8x squared. Similarly, down below, there's a factor of 2x in everything, so I'm going to factor that out. I'll need an x squared to get this term. I'll need 3x to get this term. And I'll need minus 4 to get this term. So that was pretty good. Let's see if we can keep factoring the quadratic down here. So everything else I'll just rewrite. And then hopefully I can factor that into two linear factors easily. We'll just try that visually. So there's an x and an x. Whatever goes in the last terms I have to multiply together to get me 4. So I'm just going to try 4 and 1. And when I do the middle terms, they're supposed to give me 3x when they add up. So 4x, 1x, I think if I make it plus 4x and minus 1x, that will give me 3x. And just checking 4 times negative 1 gets you minus 4. So now we've factored this expression completely. Let's look at the domain now. That's one of the advantages of doing that factoring. We can now see that this denominator will be 0 when x is equal to 0, negative 4, or 1. And so the domain consists of all real numbers except for those values. We have to exclude them from the domain to avoid division by 0. You are allowed to cancel common factors in a rational expression because the division and multiplication are compatible operations. These individual things that are being multiplied, those are factors in the numerator and denominator, and I see a factor of 2, I see a factor of x, and I even see a factor of x plus 4 that we can cancel out. So my original expression is equal to this factored version. I'm going to cancel the 2 and x and the x plus 4. That leaves me with just x in the numerator. And I'm going to cancel all of that in the denominator. I'm just left with x minus 1. These two expressions are equal, but you have to be very critical of this equal sign right here. They're equal on their common domain. What I mean by that is in this expression, I can plug in 0. I can plug in minus 4, but in this expression over here, I would be dividing by 0. So these two expressions are equal for all values of x where they're both defined. So they're equal provided x is not 0, minus 4, or 1, because this one has more restrictions on its domain than this one. But sometimes you do have a bunch of terms and you just want to do some canceling, and that will be okay if you have a single term in the denominator. So here I have a polynomial in the numerator, and then I'm dividing everything by just one term, x squared. What you are allowed to do here is split this into a bunch of individual terms. I can write this as x to the 5th over x squared minus 2x fourth over x squared plus x squared over x squared, and now I can do canceling within each one of these terms because now it's common factors within these three individual terms. So x to the 5th over x squared gives me x cubed, x squared, and 1. And now we've simplified this, so it turns out that this rational expression is equal to this polynomial expression. But keep in mind, they're equal on their common domain. This one, you're not allowed to plug in x equal to 0, where in this one you can. So this equality is only valid for x not equal to 0.